Okay, so this is the plan for today, for the next 1.5 hours. I'm going to do some statistics stuff to make sure that we all understand that we're actually doing a form of statistics and not a form of optimization per se. I'm going to talk a little bit about latent variable models and EM and variational autoencoders. So did you already have EM in this, somewhere in the course? Yeah? Okay. I'm going to talk a little bit about rate and distortion, and so why there is more dimensions than just the elbow to representation learning. And then I'm going to talk about sort of the bulk of the talk is about improving VAEs. I'm going to talk a little bit about reprioritization, although I think you already had that too, but I'll just give you my own view. It's not a bad idea to hear things a few times, I think. I'm going to talk a better prior. I'm going to talk a better encoder through auxiliary variables. I'm going to talk about a better encoder through normalizing flows and some of our own work, more recent work in this domain. And then I'm going to briefly discuss, maybe we can also change the objective a little bit, which ends up as a Wasserstein autoencoder. And then I'll transition to Bayesian statistics and look a little bit about variational Bayes and about local reprioritization. Maybe you already had that too, but then I'll give you my perspective on that too. And then I'll conclude. Okay, so in the era of deep learning, I guess a lot of new students think that machine learning is just optimization, that's it. You just have some objective function and you hit it with some optimizer, you get some answer, and then that's it, right? You're done. But I want to argue strongly that actually machine learning is actually a branch of statistics combined with the powerful tools of computer science, this optimization and computing. And we should not forget about the fact that we're doing statistics. So let's think about the data. First of all, the data are randomly distributed quantities. They're not just some numbers you stick into a computer, they're actually random distributed quantities. So let's say X are inputs like images or text or whatever, and Y are labels, annotations, and we assume that they are being generated from some probability distribution X, Y, and Y through N, 1 through N is indicating the data points that we are sampling. And then we can write down a bunch of objectives to maximize. So here we have, let's say for unsupervised learning, we can just write down the log probability of these data points under some probability model that we parameterize by theta, and then we maximize this over theta. And if we're doing supervised learning, we can write down again a probability for predicting y given theta. So now this is a conditional probability model. Everything is conditioned on x. Again with some parameters, and we're maximizing this over theta in order to maximize, the probability of the labels of our model or of our data. We don't have to use, log probability. That's just one metric. We can just write down an arbitrary loss function in more generally that compares the data yi with a prediction of the label, when we stick in some xi, which is the data point. Right, so this is basically any loss function you could put in there, and we minimize. So this looks like an optimization problem, and it is an optimization problem. But there's also something important behind it, which is that it's a statistical inference problem. And the reason I'm saying that is, for instance, there is this thing like overfitting. I'm sure you all know about it, which is you really shouldn't optimize your parameters more precisely than the scale at which these parameters, these estimates theta at the optimal values of these thetas, once you've optimized it, they fluctuate under, changing the data set. So let's say I have two data sets, xy, 1 and then xy 2. And for both of them, I compute my optimal theta. Then they're going to be a bit different, right? And on any particular data set, I shouldn't want to optimize at, more precisely than the scale at which these theta fluctuate under, changing the data set. So otherwise you're starting to overfit. And so this really is at the core of the fact that this is a statistical problem, not an optimization problem, right? Because you really should think about, what happens when things are, when my data set is changing. So to drill that down a little bit more, this is, I think, the most important concept in machine learning, which is the Bayes-Variance tradeoff. And maybe for the simplest possible example, let's say you're doing some regression, you're trying to predict some real value y with some function f of your input, and you know that there's some additional noise to y if you do your measurements. And so then you can look at the error, your estimation error. So there's some f hat, which is some procedure to estimate that function f. And the total error is going to be the true y minus your estimate of that y, f hat, and then you square it, and then you do the expectation over all possible x and y, right? So the distribution over the x and the y that the data were sampled from. So that's the error, and you can decompose that error into 3 terms. So this is the label noise term, which is this. You cannot reduce it because it's basically the intrinsic noise in the labels, and so there's no way you can sort of reduce that. So that sigma here appears here in the error, this irreducible error. But then there's these 2 terms, which is the first one is the difference between the expected estimate f minus the true function f. Now that we call the bias, because that's basically the systematic error that you're making. If you have a very simple model, and this is going to be a big, error, because your f hat cannot actually model the true complexities of f. So that's what we call the bias, is bias squared, because this square here. And then the other one is, it only depends on our estimate, is basically the variance of our function f itself. So f hat minus the expected value of f hat squared, and then taking the expectation of that. So that's basically, if I would redo this estimate for a new data set, this f will change a bit. And this is the change you'll have if you will change your data set again and again and again. So these are these fluctuations I just talked about. But they both have an impact on the error, and they trade each other off typically. So for instance, if you have a very simple model, then this will be big, and this will be small, because for a simple model, the fluctuations aren't big. If you have a very complex model, then this one will be very large, and this one will be very small. And so they trade each other off. So you can sort of, maybe view this in this way. So you have, like, you want to hit the target. Every pointer is a model that you train on a separate data set. If you have high variance, very complex model, for every data set, the estimator will change a lot, and you'll sort of have an error because it spreads around the target. If you have a bias, then you can't actually model this thing, but the spread isn't big, but the offset is large, right? And then, of course, both can go wrong, and then you're here, or both can go right, which you're here. If you have exactly the right model, the right inductive bias, then you'll get somewhere there, right? And typically, this is the trade-off. The model complexity increases. 2 things can happen. The bias typically goes down, and the variance typically goes up. And there's some optimal model complexity where these things are optimally traded off. Okay, so I think that's perhaps the most important concept in machine learning. And there is a similar concept in Bayesian learning. So let me quickly review Bayesian inference. So did we all do Bayesian learning already in this summer school? Everybody, when you look at this, you sort of immediately understand what's going on here, right? So you have a model, like this is the same kind of likelihood model, data x given theta, and a model class m. And then there's a prior over your parameters, and you integrate over all those parameters, and that gives you the evidence for that model, the probability of the data for that particular model. Then the most important object is the posterior distribution, which you can just compute using Bayes' rule. So likelihood times the prior, and then normalize it. And then if you do predictions, you're going to do a prediction basically for a data point x, but not on a single estimate theta, but you do it on a whole lot of thetas, and you weigh each theta by the posterior distribution that you computed. And then if you want to compute the total evidence, you have to also sum over the models, the different models and their probabilities in the prior. You can also compute a posterior over models. For instance, for model selection, you then sort of compute this using Bayes rule. Okay, anyway, so this is the sort of equivalent of sort of Biasvariance trade-off in Bayesian learning. So when you compute, let's say, this P of X given K, so this thing here, the evidence for a particular model, which tells us how good is that model. If you have a very simple model, so here on this axis is basically all possible data sets. So it's like a high-dimensional object clearly, but you know it's on one dimension here. So this is sort of the axis where you know you can write, you know, a point is one particular data set. And if you have a very simple model, then this peaks at a particular data set, right? So for this posterior, or this evidence is going to peak, you know, it's going to give high probability to very particular data sets, but not to every data set because it's a very limited, simple model. If you have a very complex model, it can spread, you know, it's so complex, you know, it can actually spread its probability over many more data sets because it can model basically every data set because it's so flexible. But then because it has to spread, it's you know, it's normalized thing, so its probability has to come down everywhere a little bit, right? And then there's some intermediate one. But if your data happens to be here, right, then if you have your bias clearly is, you know, you have the wrong inductive bias and you're peaking at the wrong data set, and so this is actually a very bad model because of bias. So here, this model is very complex, but you know it will cover that data point, but because it had to normalize over all the data sets, it will actually have a low probability for that particular data set as well, right? And so this intermediate one will then be the one with the right complexity. Of course, the best one would be if if this thing would actually sit right on top of it, but then that requires you to know precisely what nature looks like, and we're all making mistakes when we're doing modeling. So this again is Biasvariance trade-off, but then in a Bayesian setting. And I think this is one of the most important concepts again, so keep that in mind. So bias and variance will be a recurrent theme throughout this talk. And then another sort of high-level concept I want to sort of discuss with you a little bit about is this idea of discriminative versus generative modeling. So machine learning, so this side is sometimes also called black box modeling, or, well, let's say, you know, discriminative modeling. And, you know, lots of models that we all know and love are in here, like deep learning, kernel methods, random forest, boosting, right? So these are things which directly map from your input to your labels Y. So it's a direct mapping from X to Y. And on the other hand, there is what we call generative models, which actually directly model the generative process of the data in the input space, right? So let's say we're going to try to model, you know, how images are generated, or how text is generated, or speech is generated. So you can put a lot of expert knowledge in that, right? Because you can think about, you know, what is the statistics of images, and, you know, so you can use lots of sort of unlabeled data to try to discover the statistical structure of the input space. Right, and so that's sort of generative modeling. Maybe you have different models for different classes. If you're interested in discrimination, you could say, you know, I have a sort of a Russian language, and then I have sort of Dutch language. I have two different models for both of them. Now I get an actual input, and now I'm going to use Bayes' rule to figure out whether, you know, the Russian model or the Dutch model fitted, you know, that sentence that I'm seeing better, for instance, right? So that would be generative modeling. And now, you know, these are two very different, actually, philosophies, in my opinion. And in this side, if you talk to other people other than machine learning people, they are almost always on this side. So talk to an economist, or, you know, talk to a scientist, or whoever you talk to, they do this, because here they can put all their scientific knowledge and their expert knowledge. They stick it into this thing, right? Because so for instance, here, this is a simulator of a heart. Right? And so the physician can go in and stick in all this information that they sort of accumulated over the many, many years of sort of doing, you know, cardiology. They can put all that information in the simulator. So inject expert knowledge is really important. You can stick causal relationships in there. You can model the physics. typically these models are very interpretable too. If there's a parameter here, like maybe the blood flow coefficient or whatever, that's a very interpretable parameter. And so in an era where explainability is actually going to be very important, so you can think about every parameter separately, and every variable means something here, which is actually very important. It's also very data efficient because you can inject all this expert knowledge, right? Because there's so much knowledge already in this model, it's going to be very data efficient. Of course, the model has to be right? I mean, that's the other thing. So in other words, here, there could be this bias, right? Because I'm sticking in a lot of knowledge, and if the knowledge is wrong, clearly I'm going to make mistakes, and that's this bias. If it's, but if it's right, I can use a lot less data to learn well. It's also robust to domain shifts, and this has to do with these causal relationships. For instance, if I have a model to predict accidents, and this is actually a true story in the Netherlands, if I want to predict accidents, then you can look at correlations. So you can say black cars are more often involved in accidents than other cars. So let's raise the insurance fees for black cars, right? So that's you can do that, and statistically, there is a correlation, so it makes some sense. But now, if you go to Russia, maybe in Russia, red cars are the ones that are actually much more, people like red cars more that drive fast. Right? And so now this model, this correlation doesn't work anymore in Russia, right? But if you would model the underlying, very causal variable, maybe the sort of testosterone sort of level of the male that's driving the car, for instance, then in fact you can actually shift your model from Russia to the Netherlands, because in both these countries this causal factor is the same. And the last thing is facilitation of sort of unsupervised learning. So this is a generative model, so it works for labels, and if you add labels and non-labels, so you can use the same model to also model your unlabeled data, and you can combine these very efficiently. So I'm not saying we should all be doing this. Clearly, this has made a lot of sort of advances over the last years, especially because deep learning has started to work so well. So the good thing about this is, in fact, that we have very efficient training algorithms for this now, and they actually also solve the problem you're trying to evaluate, right? Here you have to do Bayes rule, which is a clumsy and complicated thing you have to do in order to compute y given x. Where here you're immediately modeling y given x directly, and so you're solving the problem that you're eventually going to test on, and that's a big benefit. And so, so I'm saying, so this is also good, but then the question is sort of, how do we combine these two things? And I'm going to argue that the variational autoencoder is something that, tries to combine these two things a little bit. Okay, so now there was sort of the introduction. Now we're going to talk a little bit about latent variable models. I'm sure you have had this too. Now, you can either try to model your problem directly on the input space. So x's here are the sort of observed variables, x1 through xt. And you can try to write down a model directly on those x's. But it's typically a lot more convenient to model them as a bunch of latent causes that generate those x's. So you can write down a probability of x given z, and then a probability of z. So this sort of assumes that for the phenomenon in the world, there are causes that we don't observe directly that are actually, causing the things we see. For instance, we see the pixels of an image, right? But it's very hard to model directly those pixels. But you could say, well, there's objects in the world, and the way that we observe is basically the objects. We model the objects, and then there is some physical process that maps that object, the light rays that scatter off these objects onto a camera, and then we're actually measuring that, right? So these are then, z are the objects, and the x's are the pixels in the camera. Right, now doing that is great. It's just that when you have to learn, you have to get, you have to learn this p of z given x, which is actually a very difficult object and a very intractable object typically to deal with. Okay, so then there is this elegant algorithm called expectation maximization. that we can use to learn this model P of x. So now I'm looking at a model without labels. So x in this case is just sort of, I'm trying to do unsupervised learning with x, but this goes very similar for a supervised model for y given x. And I'm going to try to maximize the probability of x given theta over the parameters theta. And now this is going to be frequentist learning. So it's kind of important to keep this in mind. This is not Bayesian learning. I'm treating my parameters as not as random variables, just as parameters. I'm going to try to find the maximizing value for that parameter theta, right? And the confusing thing is sometimes when you see a prior here, and you see posteriors here, and when people hear priors and posteriors, they think, oh, this must be Bayesian. And in fact, the problem is that there's this thing called a Bayesian network, which looks like it's a Bayesian model, but it's not at all. It's like a frequentist model, but it uses Bayes rule, and then it's called a Bayesian network. So don't get confused about that here. So theta are the parameters, z are the latent variables. Now they are random variables in this case. And of course we can, given that I wrote down this model here, I can stick that in, and I can write down, the definition of this x if I model it with latent variables. And then there is this Jensen inequality, or actually you don't have to derive it through Jensen inequality. I'm just assuming you've seen that derivation already. You can now lower bound this log evidence by introducing this new distribution Q, which could be anything you like, but the more it looks like the true posterior of z given x, the better. The bound gets tighter in that case. In fact, this is the gap between the true object and the bound. So if you can get this down to 0, if q z given x is equal to p z given x, then the gap is 0, and you'll be good. But in principle, you could make q a distribution, a family of distributions that's more tractable. And so here we have, an energy term, which is the model averaged over the posterior q of z given x. And then there is also this entropy term here for the q to make sure. So this term is there to make sure that this, if we only use this term, the q will just collapse to a delta peak at one particular z, because this term doesn't like stochasticity in z at all. And you need this extra term to make sure that z remains stochastic. Okay, and then the EM algorithm, which when I learned it was a very complicated procedure. The way it was introduced and explained was actually very complicated. Now becomes almost trivial, which is why I like this derivation so much. It's basically just two steps, the E and the M step, and it's just looking at this equation and saying this is the bound. So this is, we call this B. It depends on the parameters theta of the model that we're trying to optimize, and parameters phi of the sort of approximating posterior distribution. And we're just saying, well, let's do coordinate descent on this B, or ascent in this B. So we first maximize over phi, which is we're trying to get the q closer to this posterior here. And then once we're done, so that's the E step, we do the M step, which is we're now starting to improve our model theta a little bit, given that we fix our q. And we just iterate that until the whole thing converges. The problem is, of course, it might very easily get stuck into local optima and such, and all of these problems don't go away with this procedure. But it's a very convenient way to think about learning in the setting of graphical models. Okay, so then when this was introduced, people actually didn't write q of z given x, people wrote q of z. And there was a good reason for it, which is that they basically had a different q distribution for every data point n. So basically every data point came with its own parameters phi n, okay? And that was actually a bit troublesome, because if you then have a new data point, if you're going to test it on a new problem, you have to optimize, you have to figure out what those parameters are, and you have to do inference over those. So that was actually quite cumbersome. And so there is this trick called amortized inference, which basically says, so I don't want to have a separate q distribution for every data point z. What I would really like is to have a function or an encoder which takes a data point and maps it through some kind of, well, mapping or neural net, if you want, or a probabilistic neural net, to give me, the probability of z for that particular data point x. So in other words, at test time, I can very quickly stick in a new point x in here and generate my embedding z for that particular z. And now the phi are shared between all the data points. So there is not a phi for every data point separately. There is now a phi. There's one set of phis that's being shared between all the data points. So that's very convenient at test time. Okay, so decoders, we have a decoder. So the model looks like, again, you have a prior over z. You have a decoder model that gives you x given z. There's an encoder model, z given x, and sort of they're using this variational EM procedure, they're jointly optimized, but now there is a single set of parameters phi. Okay. We need to make one more step to get to the VAE, which is we're going to have to think of when we, in the graphical model era, we wrote down these kind of bubble diagrams, which was conditional distributions from x to y, where these are actually random variables. And in deep learning, we typically use, in those times, we used very simple conditional distributions, like an exponential family distribution or something like that. So we basically moved towards coming up with very complex conditional distributions, which are parameterized by a deep neural net. So now x goes in here, you map through many layers of sort of deterministic units. So these are now no longer sort of stochastic units at this point, but deterministic units. And there's some output, and then that's y, right? And actually, you have to predict the parameters of a distribution, let's say the mean and the variance of a distribution, right? And then this is, you can write that as a conditional distribution y given x, right? So now, we can use our graphical models, but then we are going to use these more complicated conditional distributions. And so the only difference is now that these lines here, we're going to dpify, which is we're going to stick in a neural net here. And basically now we have arrived at a variational autoencoder. There is a prior over z, then there is a whole set of deterministic layers of a neural net that predicts the parameters of a distribution. So it could be the mean and the variance for a normal, but it could also be the probabilities for a multinomial distribution, or whatever you want to, whenever distribution we're sticking in here. And then we can, once we have the parameters of the distribution, we can then write down what p of x given z is. And we did the same thing in the reverse direction, but we're going to assume that z is a normally distributed random variable, and so we're going to predict the mu's, the means, and the sigmas to get a normal distribution over the latent variables. Okay, so here's a little example how so variational autoencoder could look like. So let's say I'm in a hospital environment where I have sort of images of echocardiograms. This is like some heart image where you look at the flow of blood through the heart. So that's X. I sometimes have a label. Sometimes I know this person is sick or not. Maybe like some problem with the heart valves or something like that. That's Y, but not every time. I know this. I know half of the time. I know the hospital, S, so that's an observed quantity here. And I have these sort of set of latent variables that I actually don't know. I'm just going to infer them. I don't have any interpretation for them or something. They have to sort of emerge by themselves. Then I push all that through a neural net, and there's some sophisticated model to produce images of a heart, right? You could put all sort of stuff in here. You could use physics, you could use causality, you could use expert knowledge. So in fact, this could actually be some complicated simulator here instead of some neural net. In fact, it's probably a lot better model than a neural net. Right, and then there's the encoder, which goes from everything we observed, which in this case is the image, but also the hospital. Again, pushes through some other neural net and predicts, let's say, the z values and the y values. In this case, I've structured it to first predict the latent variables, and from the latent variables, predict the labels. There's a couple of things you can do with this. The first thing is that, if you don't observe y, you can still incorporate it in this model, right? You can still predict the y in the EM algorithm, because the EM didn't need y. So you can just predict it in this, flow, and then, learn from you infer it, then you stick the value that you inferred in here, and you can sort of learn using the M step here. But if you know why, you can clamp it. You can sort of fix it here, and then you have more information, and then you can incorporate it in your model, right? So you can sort of mix both labeled and unlabeled data. So that's why I said these kind of models are good for semi-supervised learning. Yeah, so maybe that's all I wanted to say here. Oh yeah, so yeah, you use expert knowledge. So okay, so you can also use this as your final discriminator, right? So these and these are trying to be each other inverses. So this is the generative model is going to help as some kind of regularizer, help train this discriminative model, and the discriminative model is needed to learn the generative model using this EM, right? So they help each other. Yes.
There were a couple of recent works about invertible neural networks, which is like fully invertible. So could we possibly use the same invertible model both for encoder and decoder in the different directions?
Yeah. So there's this RevNet and iRevNet, I think you're talking about. Yeah, so you can make all of these things invertible, and then in fact you can use this and this inverse here directly. Yeah, you could do that, certainly. That's a good idea. I think people probably did things like that already. In fact, I think maybe the latest paper by Dirk Kingma-Glow is of that kind, I think, because he used something like an invertible model to model this. Okay, so I want to emphasize that it's, of course, then when you're trying to do this, this is not like rocket science, and people have thought about this before. When you're trying to implement this, you quickly find that it's actually not easy to learn these models. And so then you get down to the details. So again, I write down the bound here as a function of Q, but it's also a function of these parameters theta. So if you write down the bound, so it's flowing off, unfortunately, on this side. So there is a gradient here. So here I'm computing the gradient with respect to phi of this bound. And if you compute that gradient, then if you hit this term, you're going to get Q gradient phi log Q. So that's, you can verify that you'll get something like that. And then here, you can keep everything as is. In fact, you'll hit it here too, but that term actually disappears because it's 0. So basically, this is the most important term. But then you figure out that, well, I can't actually do these integrals because this is a complicated integral. Even though it's a normal distribution, it's still a complicated integral. And so now you have to sample from this z given x, right? And so, okay, we can sample very efficiently because it's a feed-forward neural net. And one way to think about the advance of sort of amortized inference over what we did before with variational inference is that we sort of let go of that we should be able to exactly integrate over these queues, but now we only require that we can sample efficiently from them. So we assume we can sample efficiently from this, but that introduces variance, right? Because now it's random process. I'm going to compute expectations by samples, and that will introduce variance. Also, this is typically like a very large number of terms here because this is the data set X, and so this is a sum over all the data points. And so again, we're going to have to subsample a mini batch from the data points. And again, that introduces variance. So now we have two sources of variance for the gradient estimator. And that's why if you do it just like that, it's not going to work. And I think that's why this research stalled maybe 10 years ago. It's very hard to get it to work. Okay, so this is the high variance, and there's ways to to overcome that. I'll quickly talk about that. Okay, so VAEs clearly have a number of issues with them. As I said, we need to reduce the variance during learning, and there's a couple of things that people have done, or a whole lot of things people have done to do that. I will only be very brief about that. Other things that people have discovered is, in fact, that these models, VAE models, can actually produce very poor representations. So they can be great at generating data, but then if you look at the latent variables, first of all, many latent variables never activate. They just stay the distribution for that latent variable stays very close to the prior, which basically means it doesn't do anything. And so it's very hard to get a latent representation over Z that encodes a lot of information or meaningful information about X. And so people have done things like you can put an annealing factor in front of the KL divergence to make that KL term less strong in order to make sure that it learns. Or you can do this trick like free bits that Durkheim and collaborators introduced a while ago, right? And there's other things you can probably do. But I'll discuss a recent paper that talks about rate and distortion, which basically says, well, representation learning has more than one dimension. It's not just all about the elbow. You can sort of analyze it along multiple dimensions, and that's also the way we should treat it. And then from that analysis, you'll immediately see that there's multiple directions in which you can improve the VAE. You can improve the prior, you can improve the decoder, and you can improve the encoder. And we'll look at both the prior and the encoder in this talk. Okay, so first a little bit about the reprioritization trick. I think you've seen it, so skip over it a little fast. So if you have a random variable and you model it of Z given its parents, then you can equivalently model it as a deterministic function, depending on its parents, depending on a bunch of parameters, and depending on a random variate epsilon, which you externally generate. So now the randomness is coming, externally, and this is now a deterministic function. So if we're going to compute this gradient here, so this again is writing out the elbow and the gradient on the outside, what we're going to do is we're going to replace this guy here. We're going to map it using a transformation to a standard distribution P of epsilon, which doesn't depend on any parameters. So it's a standard normal distribution or whatever other normal distribution that doesn't depend on any parameters. And we're going to do that transformation trick. So then the derivative will flow right through this P of epsilon because it doesn't depend on any parameters. But now Z will depend on the parameters phi. And so what will happen is the gradient will hit, this first term here, but it will also, because Z now depends on phi, it will hit it through Z. And here it will hit it directly here, but also through Z. And so you could argue, okay, so nice trick, but why does that actually reduce my variance, right? And this is sort of homework, and it's a very simple example to show that it could have a dramatic impact. So let's say I'm going to try to compute the gradient with respect to the mean of the average of Z, which is a normally distributed random variable, over, its distribution, right? So we all know what the answer of this is. This is just the mean, because this is just the average over Z. And then computing the gradient, is going to be 1, right? Super simple. Now, if we would just do the original thing, if we would do this, then we would get this expression. So we're going to sample S samples from this normal distribution, and we're going to compute this ZS times ZS minus mu over sigma squared. And that actually has a lot of variance. If you try to compute that, multiple times over a data set samples S, you'll find you'll get very different answers. Where if you do the reprioritization trick, again, this is like for a little exercise at home, you'll get 1 over S of the sum over S of 1, right? So that's just S over S, which is 1, and it has 0 variance, right? So all the variance is gone by doing this reparameterization. So it's a huge benefit and a huge reduction in terms of variance. So just I invite you to do this at home, and you'll get an intuition of why that works. Okay, so then on to the rate distortion theorem. So this was a paper it's called Fixing a Broken Elbow by these folks. And it basically wants to address the point that, a variational autoencoder, if you just train it with any encoder or decoder pair, does not necessarily give you a good representation. And so trying to summarize the paper here, they basically said, well, let's look at both the distortion and the rate independently as two quantities. And so the distortion is, so the P star is in this case the data distribution. So the expectation over the data distribution of, the log of the conditional, this is the decoder, this is the conditional distribution x given z, over an encoding distribution Ez given x. So that's exactly the same thing that we saw in the variational autoencoder, right? But then we wrote Q of Z given x here and P of x given Z there. Okay, but E and D are in principle two quantities that we can independently manipulate. So that's a distortion. That's basically saying if I take my input x, I map it through my latent space Z, and then I generate it back through my decoder, how well am I doing in sort of generating it back? What's the error in reproducing the input through the bottleneck Z? And then the rate is this other term in the variational autoencoder, which is basically the KL between the posterior and the prior averaged over the data. And this is something that has to do with how much, so first of all, how much does my Z change? So how does my posterior is different from my prior? Or how many bits do I need in order to encode my embeddings relative to the prior in this case? But so this is like the number of bits I require to encode my latent representation. So it says something about the amount of information that's in my latent representation. That's the rate. And then this is just the entropy of the data, and it's a fixed quantity. I can't change it. Okay, so then we're going to look at basically the distortion and the rate independently. And you can look at something like, let's minimize the distortion given a particular rate. So let's say fix the rate and then minimize the distortion. And you typically do that with a Lagrange multiplier. So you introduce a Lagrange multiplier beta, and then fix the R at a particular value, say R minus C, right? And then you minimize this whole thing. So there's an equivalent formulation where you don't fix the rate and you sort of adapt the beta so that the rate is fixed, but you fix the beta and you optimize this whole thing together. Now that's exactly what we call sort of a beta annealed variational autoencoder. So we put a temperature, an inverse temperature in front of the rate, and we minimize this whole thing over three quantities: the encoder, the prior, and the decoder. And what they show is that there's an interesting sort of relationship between this. It says that there's the mutual information between X and Z, which is really the amount of information encoded in the latent representation about the data. That's the mutual information between X and Z. So that's defined here, where the joint distribution over X and Z is defined as the data distribution multiplied by the encoder distribution. So that's what the PE is, the encoder joint distribution PX given Z, comma Z. And then, of course, there are marginals down here. Okay, so that's the mutual information between the input and the latent representation. And they show this kind of interesting relationship which says that the mutual information is always smaller than the rate, and it's always larger than the entropy minus the distortion. Okay. So, and then you can sort of plot this thing here which says that on this axis there's the distortion and here is the rate. And an elbow is basically setting beta to 1, so it's just 1 point, it's one set of points here on this graph. But they argue you should really look at the whole rate distortion plane together. And you can show, since all of these quantities are positive, surely the rate cannot go down lower than h, because h is fixed. If the distortion is 0, then the rate has to be larger than h. So the rate cannot go down larger than h with a 0 distortion. And then you can also derive basically that on this axis when the rate is 0, the distortion can't go down more than h as well. So basically this is the feasible region of rate distortions that you can achieve. You can never sit there, right? And then for a particular encoder, decoder, prior combination, when you move beta around, you're going to be on one of these curves, right? So the best curves would be like here, but typically because these are not, the correct encoder, decoder, prior triple, you're going to be on some kind of sort of curve here, and they basically say you should look at the entire curve for all beta. So for instance, if you're on this curve for a particular beta, let's say beta equal to 1, if you make your prior m worse, you're going to move to a worse rate. You can look at the rate here. If you make m worse, then you're going to move to a worse rate at the same distortion, because this distortion doesn't depend on m. Right? So you're going to now be on a different curve if you change beta again. Similarly, if you fix the rate and you just make your decoder worse, you're going to move up here, because your rate doesn't depend on the decoder, but your distortion depends on the decoder. And if you make it worse, the distortion gets worse. So now you're on this curve, right? Okay, so the point is, first of all, the lessons that we learn from this is the elbow is one-dimensional, evaluation of, how a representation learning or a VAE works. We should look at the entire, plane, distortion rate plane. And also that we can actually improve things by working both on the decoder, the encoder, and the prior. Okay, so I'm not going to talk about improving the decoder, but there has been a lot of work on that. For instance, pixel CNNs and models like that. There are very sophisticated, powerful decoders. So I'm going to leave that for further, reading at home. I'm going to talk about the prior and the encoder, right? Different ways to improve both the prior and the encoder. And so one additional intuition of wanting to improve the prior is this. So let's say so these black dots are the embedded points. So these are the embedded data points through the encoder. So they map into this space. And now I need to have like a prior that sort of covers all of these points. And no, the problem is that if these are not, and your prior is some kind of normal distribution like this, but if the embedded points are not normally distributed, then you're going to create these kind of holes where there's never any data in this latent space. And therefore the decoder never learns to generate good axes, or let's say images, if it's going to be asked to generate something from here. But when you apply this model, you're going to generate from the prior, right? You're not going to take, so this is a point that's a data point that's embedded and then perhaps decoded. But if you generate random stuff from this model, you let it dream, then you're going to generate something from this prior, which is the red thing. And if it's going to select something here, you're doing fine. But if it's going to select something here, then the decoder has never seen that, and it's going to be very bad. Okay, so that argues for having a prior that at least sort of, is a good model for these black dots. And so here is then our, so this is work with Jakub Tomczak to improve sort of this prior, to make it a more sophisticated prior. And it's interesting because if you look at this expression again, this is the elbow, this prior just sits here. These terms don't depend on it. And so, it just interacts with this encoder. And so if you just maximize over this prior, you get an expression, you get an answer, right? And it's like a silly not to actually do that then, because you can just do it, and it's the optimal answer. So if you do that optimization, you'll find that the optimal prior for a given data set is going to be the average over the data of Q of Z given Xn. So this is called the aggregated posterior. So the aggregated posterior is actually the optimal thing. And so this is a mixture, right? So if this Q is a little Gaussian distribution, then this is a mixture of Gaussians with one Gaussian on every data point. Now the problem with this is that it's actually very expensive and it doesn't scale very well, because if you have a billion data points, and this is going to be a billion dimensional mixture, and that doesn't scale very well. So you need to do a trick in order to make this scale well. And what you can do is you can introduce pseudo data points, UK. So here they are. These are things that sort of data points that we can learn. We're going to move them around in the input space, and they're going to put themselves on locations such that they cover, the data points in the input. And of course we have k of them, so we average over k. And then, so these folks, same people from the paper just discussed, actually generalized this a little bit by putting weights in front of those, so now you have really a mixture of Gaussians with actual sort of, prior distributions over the mixture components here as well. Okay, so you can just train all that jointly. So you can stick this solution back into here. And then the interesting thing is, of course, that now this depends on Q as well. So now when you do an optimization step over Q, it will hit you here, but now also here and here. So all of this gets coupled together. And indeed, when you do this, you'll find that you get a lot better, VAE. So if you start generating from this VAE, it only starts generating from points that it's actually been trained on. Okay, so then we're going to look at improving the encoder. And this is a trick that's originally proposed by Salimans and Knowles. Basically what we do is we're going to say, well, okay, so we have a model over X and Z. Let's introduce some more latent variables, auxiliary latent variables Y, because it might make our life easier. Okay, so let's say I'm going to enhance my model distribution by Px given x, z times a new R of Y given xz. So I can always cook up some R. It's totally free. I can choose whatever I want at this point to make this into a joint distribution over X and Z and Y. And similarly for the posterior, Q of Z given X, we're going to enhance it to be Q of Z comma Y given X. So in other words, just think of Y as another set of auxiliary Zs that I'm adding to the problem. Now why is this a good idea? It's a good idea because my new Q of Z given X, right, is now going to be this integral. And even though these objects can be very simple, this integral can actually be quite complicated. So now, if I'm able to handle, learning with this, with this new setup, I can actually have quite complex Q of Z given X. It doesn't have to be a very tractable distribution because now only this thing will have to be tractable. Okay. So then we're going to, and actually this is simpler than it looks like. So we can now write down the new bound for the problem with the additional auxiliary variables. And it's just exactly the same. Just throw the y's and the z. So zt is now the original z. So throw the y's and the z's onto one pile and just treat them as one big bag of latent variables. Then what you see here is just the ordinary elbow, right? It's Q of the latent variables given the observed variables. And then this is our model. It's the joint over X and Z and Y. And this is our posterior, which is the posterior over Y and Z given X. So that's the elbow with the addition of the auxiliary variables. And you can show that, in fact, that is a lower bound on the lower bound that we're used to if we would use this Q of Z given X. So if we would write down our elbow for this Q of Z given X directly, then you can show that this new objective is actually, again, lower bounding, the original elbow. So we're getting looser. The bound is getting looser by this trick, right? And you can think maybe that's a bad idea, but actually it's a good idea. And the reason is that when I wrote down this L, I had to use tractable distributions Q of Z given X. Otherwise, I couldn't optimize it. Now I'm going to use, I'm going to use these guys, and I'm going to write down a looser bound, but now my Q is going to be a lot more flexible. So in other words, we can make up by using a much more complicated Z given X by loosening the bound. So these two things work in opposite directions. And it could still be that this whole thing is actually a better bound, right, with this complicated Q of Z given X, than only looking at this with a simple Q of Z given X. Now, if you're interested in how to derive that, there is this very simple but elegant rule for KL divergences, which basically says the KL between a Q of XZ and a P of XZ you can write it as a KL between Q of X and P of X plus a conditional KL between Z given X and PZ given X, but then averaged over Q of X. And you can do this in both directions, and you can. Actually, no, you cannot. You have to do it over the Q, but you can, of course, use multiple variables. You can use 3 variables or whatever. And it's this rule, basically, which you can use to derive this sort of bound. And it's a very useful thing because you can also use it for the VAE. Okay, so that's auxiliary variables. So in a picture, basically it looks like this. Okay, so no. So instead of having one single auxiliary variable y, what we're going to do is we're going to introduce a whole lot of them in the form of a chain. And so now my y's are going to be z0 to zt minus 1. And I'm going to structure them in a chain. So I'm going to say my r of y given z and r is, it's going to be zt minus 1 given x and zt. So sorry, that's here. So zt minus 1 given zt and x. And then the next one given these two, etc., until z0 given z1 and x. So I'm going to organize them as a chain here. I'm also going to organize the q as a chain here. So going in the opposite direction from z0 to zt. So zt, again, is the original latent variables that I was interested in. And all of these are the additional auxiliary latent variables that I'm introducing. Okay, and then maybe you shouldn't go too deep into details, but you can write down the bound, more concisely like this. And there's a very nice algorithm to compute the bound iteratively. And you can look it up in the paper how that works. And basically, you can think of this as a Markov chain. You're going to use a Markov chain to actually approximate the posterior distribution of z given x. Right? Because this, if you think about this, this is an ordinary Markov chain that goes from x to z, right? Where you marginalize out all these intermediate auxiliary variables y as a Markov chain. Okay. Okay. So then there is yet another. So is there any questions, by the way? You want to discuss this a little bit? Is everything clear, or? So that's one way to improve the encoder. There's also another elegant way to improve the encoder, which is through what we call a normalizing flow. So the first observation is that the variational autoencoder, in fact, it predicts the mean and the variance of a normal distribution using a very complicated neural net, but then it's still a normal distribution at the end, right? Because we're going to still draw z from a normal distribution with that mean and with that variance. And so it's still a very simple normal distribution in the end. So one question you could ask yourself is, can we actually make that distribution more complicated than just a normal distribution? And there's this neat trick which was introduced by, I should have it somewhere. Okay, so this is Rezende and Mohammed. I think the citation is somewhere. Which is called normalizing flows. And the idea is that you basically do a transformation of your variable z. So if you have a z and you transform it under some invertible function f, then the density for the new z prime here is going to be the density of the old z times this, basically this volume factor. It's a Jacobian. Is the determinant of this Jacobian, which is all the partial derivatives, basically. The matrix, it's a matrix of every function f with every, zi, all these derivatives in a big matrix, and you compute the determinant and then the absolute value, and that's the thing you need here. The thing that what this models is basically the stretching of the transformation, right? Because let's say if you have a uniform distribution between 0 and 1, and I transform x goes to 2x, right? Then my space is going to be extended between 0 and 2, but clearly the density is going to be a half because it has to integrate to 1. And so the transformation x goes to 2x stretches space by a factor of 2, and so you have to compensate by this Jacobian then, which is going to be a half in this case. And so the trick now is to say, well, let's do k of these transformations after each other. So we first map using a normal VAE mapping to some normal distribution. You see some mean and some variance for the first z. That's the standard thing you do for a VAE. But then you're going to apply, k of these f transformations in a row. And then you can show that the Q, the encoder distribution, is going to transform like under this type of rule. Now I have a log in front. Log of q minus the sum of the log of these determinant Jacobians. Okay, so it's not hard to derive. It's basically you do it k times and you have a log and it's a sum over those k Jacobians. Because here you basically get a product of these Jacobians. Okay, so then the full sort of bound is going to look like, this is the usual bound, so this term doesn't change. Here you get the first one, the z0, and then you have this sequence of Jacobians, log Jacobians that are still there. Okay, so here's the citation. So planar flows basically uses this particular function, which is parameterized by w and b and u, right? And it's a convenient one because you can compute the determinant really easily. So you can use a rule that says that the determinant of I plus something is 1 plus, switching some of these transposes around. So that's a very easy and convenient way to compute that determinant, right? The only thing you should note here is that it all goes through this function h, which is a scalar. So basically you get z, which gets mapped to a scalar, then through a nonlinearity, and then mapped out back through u. So everything goes through this bottleneck of one neuron, and that's quite limiting. So this one neuron bottleneck is quite limiting. So here's something that we did to improve that. So there is actually a quite natural generalization of this idea, which is to say that, so now it looks a lot like a normalizing flow, but now B is a matrix that maps from the original D-dimensional space to an M-dimensional space, where M should be smaller or equal than D, but it could be equal to D. And then H is a vector function on all of these input values, and then again an A matrix to map it back out, right? So this is a direct generalization, and then there is this Sylvester determinant identity, which basically says if you need to compute this determinant of I plus AB, you can use the determinant of, in the M space plus BA. Okay, so you can use a similar thing. Now we still have to choose A and B, and in order for this to be invertible, because this only works when the function is invertible, otherwise you cannot do this trick with the Jacobian, you need to put some restrictions on what A and B can be. So A is going to look like a QR decomposition, and also B is going to be looking like the transpose of a QR decomposition. R and R tilde are two different upper triangular matrices. And Q is basically a collection of columns which are orthonormal vectors, right? So the Q's are orthonormal vectors, which is they're orthogonal and they're normalized to 1. And there's M of those in columns. So this Q is kind of like, looks like an orthogonal matrix, but it's D times M. And these R's are upper triangular matrices. They can be arbitrary. Now, under these conditions, this thing is invertible. You can prove it. And basically, the set of transformations looks like this. So Z comes in, and then there's X, which determines through a function all of these parameters of R and Q and R tilde. So that's sort of the amortized part of things. These are the parameters that go into the transformation, and then you go to the next Z prime. Okay, so it's a generalization, and you can show that let R and R tilde be upper triangular matrices. H should be a smooth function with bounded positive derivative. And if the diagonal entries of R all satisfy, R I times R tilde I larger than -1 over the infinity norm of the derivative of H, then in fact, and R tilde is invertible, then in fact the transformation is, the whole transformation is invertible. Okay, so this is a direct generalization of normalizing flows. Okay, so that's that. There's other ones. There's also the inverse autoaggressive flow, and there's a bunch of other ones which also generalize on the normalizing the planar normalizing flows. Okay, so now we have finished sort of improving the VAE by looking at improving the prior or improving the encoder. Now we're going to look at, could we also do something by change the entire objective? And in fact, I just want to point out this quite nice connection between GANs, generative adversarial networks, and variational autoencoders. This is a paper by Tolstikin et al. From Shokop's group. I pronounced it very bad, I know. I see people laughing. This is what they call the Wasserstein autoencoder. And the idea is really simple. Going back to this picture here, the VAE basically says, it tries to enforce that every Q of Z given X looks like the prior. So for every data point, Z given X is drawn to be close to the prior. So you need a lot of force to try to be different from the prior. And the question is whether that's a too strict condition. So people have said, well, why actually not just, look at, the fact that these embedded vectors just distribute like the prior? Because if you remember my previous argument for improving the for improving the prior was, well, there's these holes, and these holes are bad because the generative model isn't trained in these holes. Well, if that's the problem, why not just say that, okay, the embedded vectors, the embedded data points should just distribute like the prior, then that whole argument can't happen at all. And that's exactly what this, this Wasserstein autoencoder does. Now, there's a whole lot of cool theory behind it. Okay, let's first look at what you actually have to do. It's a tiny change. So you look at the variational autoencoder. So the term is this. So you KL between Z given X and P of Z for every X, but then averaged over P of X. And you're going to say, let's move this P of X inside the KL. So now here, there's the aggregated posterior, right? It's just Q of Z, but averaged over all the data. That's the aggregated posterior. That's kind of the distribution of these black dots. And prior, P of Z, which is the red thing. And now we're just going to say that the embedded black dots should be distributed according to this prior P of Z. So you really have to not change very much if you're going to use this KL for using that trick. But it turns out, more generally, it looks like this. So there is X is the data point. So you embed Z by going through the encoder Q, Z given X. So that's how you generate your Z. And then there's the generative model, which oftentimes is the deterministic map, going back to X. So this is the distortion, again, right? And you want the distortion to be small. And then this is the distance between the aggregated posterior Z and the prior P of Z, okay? And you can put any distance here. You would even put again here in order to enforce these two distributions to be the same. If you put again here, then it's called what's called a adversarial autoencoder. But you can put anything else. You put the KL, it's very close to the variational autoencoder, but you can put anything else there. You can put, I forgot the name. Okay, I forgot the name. But there's other useful distances here between distributions that you can put there too. But the nice thing is that there is a very, this expression, if the distance is actually minimized, you can then show that it is the dual of a optimal transport problem between the data distribution and the generative distribution. So this is a different distance between two distributions. It's an optimal transport. It's like, how do I move mass from one distribution to mass to another distribution, right? How am I going to move that mass, and the minimum, amount of, effort I have to do to move that mass from one distribution to the other distribution is going to be my distance. And people have argued that's a lot better distance to use. So you can show that, that will create the Wasserstein GAN, but if you look at the dual, it will actually create, this objective, which looks a lot like the normal VAE, but then, you're now forcing the aggregated posterior to be close to the prior, right? And so you see there's a beautiful connection actually between GANs and VAEs. Although I should also say that when you actually try to minimize this thing, you don't solve the problem that the VAE typically, that bothers the VAE typically, which is blurry images. In fact, if you do this, you get maybe a little less blurry, but not nearly as good as when you train again in the usual way with an adversary. Right, so note that this is actually, you know, a nice min-min problem. It's not a saddle point problem. This is just an optimization problem. But if you do it this way, even though it might be theoretically equivalent, it's actually not. It doesn't do as well as an adversarial autoencoder in terms of getting crisp images. Although, you know, the coverage, I mean, there's always a trade-off between coverage. Do I cover all the data points and blurriness? Yep.
Sorry, isn't the problem with blurry images on the output not so much that there's a problem with the rate and distortion, but more that you're using a normal distribution on the output, which is not really the distribution from which images come from? If you're just using a factorized normal on the output with a single sigma, or even a factorized sigma.
But this, so actually look, if you look at this, I mean, you mean the normal for these guys, or do you do a normal for the generative distribution? Because here, this is just a deterministic function now. This is in fact not, you know, you're not predicting the mean and...
Right. You're just predicting the x's for the image, right? Okay.
Yeah, so this could be a normal, but it could be anything else as well. But in fact, this could be just, you know, it's called implicit distribution. You have some prior p of z which is random, and then a deterministic function to map to x. But even if you do that, you don't get rid of the blurriness in this dual formulation entirely. So I think there's more to it, and it has probably something to do with the optimization procedure itself. Okay, so this was all I was going to say about VAEs and sort of how to improve on VAEs. I'm also going to say a few things about Bayesian inference, time allowing. So I'll just use the last 15 minutes to say a few things about that and see how far we get. So the first thing, I already said a little bit about it. Maybe a question to the audience is, you know, what's the difference between a prior p of z over latent variables and a prior p of w over parameters? Right, so you know, why are these things actually conceptually quite different? If, you know, in this case you're in a Bayesian framework, and in this case you don't you're not necessarily in a Bayesian framework, you could also be in a frequentist framework. Does anybody want to take a guess why this is different? So, you know, one hint could be, you know, training P of W, is this something that we should be doing? Or should we leave P of W alone? Sorry? About learning P of W, or about W at all? Yeah. Yeah, so in fact, we shouldn't care about it, but if you're a Bayesian, you should probably, it's not even allowed, because your prior over your weights is your prior over what your model is, and your prior is before looking at the data. So then if you start to learn this thing, you're now going to mess with your uncertainty over your model, because you look at the data and then you adapt your prior. So like you peek at the data and you say, oh, well, actually the data looks like this, so maybe the prior should be more like this. Which means that you're not going to get the true estimate of your uncertainty over the model. Now, writing down a P of W is not very trivial, because it should actually reflect your prior idea of what these parameters should look like, and for a neural net that's very complicated, obviously. So in practical terms, people do train them, and that's called empirical Bayes. But the most important thing is that, you know, being Bayesian is actually a little bit of a different philosophy, because you acknowledge that the world is subjective. So that if I train a model, if I look at the world and I write down a model, it could be the same model that you write down, but if my prior is different than yours, then you end up with different predictions than I end up with. And that's totally fine, because it's subjective, right? It's not actually, there is no, you know, it's not necessarily that, you know, we should agree on it. We can have completely different conclusions, but that's fine, because they depend on our prior assumptions. So it's a bit of a different philosophy, which is sort of the second thing. And then already answered this one. So a Bayesian network isn't Bayesian, because It just treats parameters as parameters and not as random variables, but it uses Bayes' rule, and then that's called a Bayes network. So why would you even be interested in Bayes? Because it produces actually a little bit of overhead in computation. It does provide you at least with some sense of protection against overfitting because of this averaging over all possible models. Often people say this is because you have a prior. And even if you would do map estimation, your prior acts like a regularizer, and then that is giving you some level of protection to overfitting. That's true. But the biggest benefit comes from the fact that you actually integrate over your posterior. And that integration is actually giving you a much bigger protection against overfitting. Then there is uncertainties over your model, right? I look at the data, I have some model. The data information that's in the data should move into the parameters of my model. And the more data, the more certain I'm going to be about those model parameters. Given a finite data set, I don't know perfectly what those parameters should be. So there is some parameters might still be completely undetermined, other parameters might be much better nailed down by the data. And that sort of difference in how certain you are about your model parameters is reflected in these posterior distributions. And then more recently, there has been a very cool application of Bayesian learning in compression. I'm pretty sure you'll get people from this group or Dimitri Vetro's group talking to you about that. Because you can use sparsity-inducing priors on your weights and your activations, and by using Bayesian learning, a lot of these will prune away if they're not useful. So in other words, if there's weights that are not contributing much to the predictions, then by this prior, they're going to be removed from the model, and that will give you very nice compressed models. So there's two families of Bayesian posterior inference. There's probably more, but these are the two major ones. One is again variational inference, and this is very similar to the things we just wrote down. There is some variational family that you write down. It's more restricted than the full set of all probability distributions. And then there is your distribution typically lies somewhere outside of this class, and you're going to try to find the best approximating distribution according to some distance, which is typically the KL distance. Here you're going to have bias. So in other words, even if your data set becomes infinitely large, you're still going to have that difference here. So again, here's the Biasvariance problem again. We've seen it now many times. And again, so there's going to be a bias that you can't overcome if you restrict yourself to this family. Now, there's also sampling, which is you're going to approximate all your averages by sampling averages or Monte Carlo averages, which basically means if I am going to average over this distribution, I'm going to first sample some points from that distribution, and I'm going to evaluate the function I want to average over. I'm going to evaluate it at those points, and then I'm going to take the sampling average. Now this here, if you do it right, if you get points from the actual distribution, has no bias. If you get an infinite number of samples, you'll get the right answer. However, the problem is that you get variance in your error. Because if you draw a few samples, then and you draw again a few samples, then the two answers are going to be different. And typically, the bias you incur here could actually be less than the variance error that you sort of incur there. Okay, so this is basically again writing down. You can write down a bound on your evidence, but now you're not integrating over latent variables, but now you're integrating over parameters. So Jeff Hinton was the first one in '93 to start thinking about doing that variationally. And it's again exactly the same sort of derivation with KL bounds that you then discard in order to get your elbow type bound, and you can write it as an energy and an entropy term. And again, you get exactly the same considerations, but now everything over parameter space. So you get some. You want to do this. You want to optimize over this Q function. But the problem is you can't actually do the integral, so you have to sample here, you have to sample there, because this is a very large sum over data points. again, lots of variance, and you can't handle it very well because the derivatives have too much variance. So then you can do the same trick like reparameterization by replacing the Q distribution, by mapping it to a standard distribution by a mapping F that maps theta to some other parameters omega, such that this holds, and then now any derivative with respect to phi just passes through this thing and just hits it here and here and here, basically there, 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 there. So that's reparameterization. The problem is that it's not enough, so 7 more minutes. So it's not enough, actually, and I'm going to at least try to explain why you need more. Okay, so I'm going to write down now the term. This is basically the for a neural net or some kind of supervised learning problem where y is the label and x is the input. And I've reparameterized it, so w is some function of epsilon, an external random variable, and some phi's. And I have also a mini batch I'm summing over. And so now I'm going to take a gradient, right? And I'm going to hit the gradient there for this term. And now there's one, so how would we actually now do the computation? So the computation could look like I draw a single epsilon, and then I have a sum over m data points where I inject that single epsilon. And then I compute the gradients of each one of these terms, and then I add them up. And the problem is that that actually is not a great idea, because you get all these terms for the data points, they all start to correlate a lot. They start to correlate because you use the same random epsilon here to compute those terms. So the variance, in other words, is very large because all these terms are correlated. You can just write down an expression to show that the actual variance of the gradient depends on the correlation between these terms. And so actually when you try to do that, the variance is very large. So there's this trick to overcome that. So okay, so you could say what you really want to do here is for every term, draw a separate w. That would solve it, right? And you can do that because you get exactly the same answer. So you write out all the terms for every data point, and instead of drawing a single epsilon, draw a separate epsilon for each one of these terms. That would solve it. The problem is that for a neural net, that's very, very expensive, because in a neural net, when you have 1,000 neurons, you're going to multiply w as 1,000 times 1,000, so that's 1,000,000 neurons. And now, if you have m data points, you have to draw m times 1,000,000 random variables to instantiate that random matrix. And then you have to do all these multiplications again. And that's m times, and that's very, very expensive. So there's this little trick, which is called the local reparameterization trick. So again, here's the bound. I'm sorry for switching between some notation a bit. So sometimes I write theta, sometimes I write w here. Okay, so here is the distortion if you want, and here's the rate if you want. And now we're gonna leave this alone because this part is usually tractable, and we're gonna have to look at this and reparameterize. And the trick to use is to say, okay, so we're gonna move. Maybe I can show it here. So there's noise on these parameters, and we're gonna move the noise to the latent variables here. So I'm gonna avoid the noise here, but I'm going to look at how that noise affects basically the distributions of these neurons, and then I'm going to directly draw from that distribution. So that's the trick. More mathematically speaking is, okay, so here is my model. I'm integrating over this big weight matrix, and I have some approximate posterior over that weight matrix. And here is, let's say, for the last layer, y given weight times nonlinearity times the activations of the units before. So that's this guy here. And I'm, basically going to add, I'm going to move the randomness over W to the randomness over Fi, which is the activations here. And I know that the activations Fi are equal to W times phi Bi. That's just an equality. So since it's an equality, I can just add another integral with an indicator function, Fi minus W phi Bi. It's mathematically just a trivial thing to do. Now what I can do is I can move this integral outside, and since this is an equality, I can, and this thing depends exactly on this, so I can replace this by fi. And since this is a normal distribution, a Gaussian distribution, I can actually do this integral over w. And then if I do the integral over w and I keep the integral over fi, I get q of fi given bi. Basically, I get, this q of w is now going to depend on fi, and I've integrated out the w. Okay, so now the expression only depends on fi, and I can now directly, I know the distribution for this fi is again normal distribution, and I can directly generate those fi's instead of the w's, which is k times m, where k is the number of neurons and m is the number of data points in the mini-batch. So that's a lot more efficient to do, and it solves our problem of reducing the variance. Okay, so then the whole thing looks like this. We have y given f is the activations here, and then there's these integrals over these posterior distributions b given x and f given b. And then there's the KL term, which is still there. Okay, anyway, so probably should stop. I'm almost out of time. There's two extensions that we looked at recently. One is structuring this prior and the posteriors as matrix normal distributions, which is a more efficient way to structure those priors and posteriors. And another one is, again, using normalizing flows to improve the flexibility of these distributions, where you write them as a normal of z times u, and then you put a normalizing flow on z. Okay, so conclusions. The first thing is, think about variance and bias of both estimators and gradients, because that's a very fundamental trade-off, and there's always either one of the two, and typically if you can trade off a bit of variance by bias, and that can help you a lot. There's more to representation learning than just the elbow. It's better to look at rate and distortion. And going from that analysis, you can also look at there's various ways to improve a VAE by looking at priors, looking at encoder, and looking at the decoder, or looking at the objective directly. Oops. A model is not Bayesian when there is a prior over latent variables, so don't confuse priors and posteriors, which people talk about when they talk about latent variables, with actually being Bayesian, which is being thinking about subjective models and that kind of stuff. So that's actually different. So don't confuse the two. And then I've talked about local reprioritization to help variance computation in Bayesian learning. And I'll leave it at that. And it's exactly 11:30. Thank you.
Are there any questions for the speaker?
Your motivation for using generative models is very, very compelling, especially because the knowledge that you put into it. But we're not really used to think that way in a causal, in a causal way. Can you go back to that slide with the heart simulator and maybe give some more examples of what sort of knowledge you can put into this, encoder?
Sorry, you're asking what kind of knowledge I can inject in the encoder?
Yes, so maybe in different domains like biology or physics or economy, anything. Because
right.
I think it's very flexible, but you just have to train this way of thinking.
Yes, for instance, in language, people have written down powerful language models of how words are being generated one by one. That's a generative. People in language modeling, actually, people use this kind of language models like that. In speech, there's a beautiful model that actually models the physical processes of producing speech. So I don't think people use that anymore. It's basically now all deep learning black box that's ruling that area. But you could imagine that at some point, those type of models, I think it is also a function of how much data you have. If you have a huge amount of data, then what you'll get is that your imagination of how the world works is going to fall short of how it really works, and then your bias is going to be too large. And if you have all that data, then your black box modeling is actually going to be better. So in that domain, actually, I think they've given up on that, although they've put a lot of effort in these types of models. Now, if you go to physics, I've been talking to, for instance, physicists who do LHC experiments. So they look at particle collisions, and they look at features that they can use to figure out whether a certain particle is there or not, right? And so they have very powerful simulators of how an actual experiment runs, so a collision, and then how does the detector work, and etc. So to get to your actual measurements, and they use that a lot. So that could be something that could be in here. For astronomers, you could think about. I've looked at models where there is sort of stars that move over time. And if you assume there's certain dark matter at certain places, how will that influence the movement of these stars? And by that, you could infer something about, the presence of dark matter in the universe. So there's like a huge domain-specific number of ways you can insert knowledge there.
So it also provides a great opportunity to go out and connect to other domains, I think.
Yeah, exactly, right? So I think that's the way you actually communicate with scientists, because they will provide you that model, right? And then you can say, well, okay, you can do that, but maybe I can help you predict, let's say, the variables or the sort of the parameters that go into that model.
And if you want to master these techniques and you know some model, it may also be a very good entrance. So you know some model and you try these techniques, and maybe you need to use some of the techniques that you've shown today, or maybe not. Maybe the simple vanilla approach works.
Yeah, so what's the question? Sorry,
not really a question, more a remark.
Okay, yes. Yeah, thank
you. Thank you.
Wait, maybe you... yeah, it's hard for me to hear.
Yeah. So one of your first slides, you talk about this Bayesian model complexity and the sort of the Biasvariance trade-off for the Bayesian regime. Very deep neural networks tend to overfit really well on small data sets, and even like on ImageNet. Would that mean that a very deep neural network that is Bayesian about all the parameters would never be able to fit on anything because of this complexity probability trade-off?
Yeah. So the question is, a deep Bayesian neural net has many parameters, and then if you would treat it in a Bayesian way, it's super flexible. So it means that the probability it can assign to any particular data set is going to be small. I think that's a good point, but then the other part is that on a small data set, you probably have that issue. Except when you put priors that will remove those parameters. So typically what people do is they put a sparsity inducing prior, or they say, well, if the variance of that parameter is large compared to the mean, then we're going to prune that out. So if you start pruning the model down, then in fact you will overfit if you want. You will fit again because you're moving your model now. But if you would have a few data points and you have a huge number of parameters and you maintain priors and posteriors which are very wide, and you start sampling from those posteriors, then the predictions are going to be all over the place because of the variance. And that's that phenomenon. You're not going to fit very well because of that. Now, I should also warn that being Bayesian about 10 parameters you can do in a rather principled way. But being Bayesian about a billion parameters is uncharted territory. We can perhaps do things computationally, but I wouldn't vouch for the fact that the posterior that we are computing is actually anywhere near a reasonable posterior. So I think a lot of research should still be done. And in fact, for dropout posteriors, it was already discovered by some people from Cambridge that they're even improper. But then, there's other ways that you can sort of, again, fix it. So I think in these very high dimensional spaces, things are pretty finicky, and we should not try to trust it too much, I would say.
So I think this is a very great explanation of variational encoders and Bayesian methods. And really, my question is: so, like you just said, that being Bayesian over like 100 billion parameters is, you know, complicated. Your posteriors may be incorrect. So, would you say that there's so the deep learning people will say, well, I have like a ton of data, and I can just take my model and train it, and I don't need to be Bayesian. I can segment perfectly. I can speech recognize perfectly. Would you say that Bayesian models need to be applied to more niche areas like the physics stuff, and that they need to also be evaluated against different criteria as opposed to the standard deep learning big models?
Yes, I think that's a very good point. In fact, for many applications, you do not need or want to be Bayesian because it actually also adds overhead to your computation. And if you have a lot of data, if you just want to be good at making predictions, then often, and you have a good regularizer to avoid overfitting like dropout, then things work just fine, and you can forget about being Bayesian. When you're interested in uncertainties, maybe at that point, you know, you could start considering being Bayesian. But also, I find maybe the most elegant application is compression. So these neural nets are extremely large, typically, with a huge number of parameters. And so the Bayesian sort of paradigm has helped us come up with a principled procedure to prune these models down to much smaller ones. And that's, I think, a very elegant application. But I agree, you shouldn't sort of, for every problem, just say, well, Bayesian is better than non-Bayesian, so it should be Bayesian, because it's harder to train these models, it's harder to do it well. You know, there's complications like, if you misspecify the model, what does that do to your posterior, and all these things, which are actually quite complicated.
Hi. Thank you for a very nice talk. I was just wondering, we've mentioned several problems with the Bayesian inference in deep neural networks. Like using Bayesian dropout causes ill-posed posterior with no normalizing constants, like having extremely large bias with variational inference, right, in general. Do you think there is too few attempts to apply scalable MCMC methods currently that we have to pay more attention to?
Yeah, that's a very good point. And personally, I also like that. I also like that sort of line of research. So personally, I've been going back and forth between scalable MCMC and variational Bayes. So in variational Bayes, you can become better in building more flexible models. In MCMC, you can be better in making sure your MCMC sampler scales well when n increases. So, for instance, if your data set gets very, very large or even infinitely large, MCMC samplers don't run because they depend on every data point for every step. But there's ways to cut things short, which is to make the MCMC step only depend on a mini batch and do an approximate sampling. Again, that's a bias variance trade-off, by the way, because you introduce a little bit of bias, but you can reduce the variance a lot because you can draw a lot more samples. And I think I agree that we should get back to that. We tried it, you know, many years ago for deep learning. It wasn't at that point working super well, but I think with the new techniques and maybe also with more computation that we have access to now, there's room for trying this again. So again, looking at stochastic gradient MCMC methods or stochastic gradient HMC, and see if that actually is competitive with these methods. I certainly think that's a good idea.
This is building up on one of the earlier questions about deep learning. It's about deep learning, the standard deep learning technique versus Bayesian models. Could you also comment on GANs versus variation encoders, when one should prefer GANs and when?
Yeah, so this is a question about variational autoencoders versus GANs. So I'm not an expert in GANs, but you know, we've worked on it a little bit. So I'm just going to cite some things that I've heard in places. So the GANs are, first of all, they are hard to train because it's a minimax problem. But if you're sufficiently trained, you can get very good, pretty results with it. But it seems that where variational autoencoders are trying to cover the space, which makes them blurry, so they want to try to put probability mass everywhere where there is data, which means that they can also put mass in places where, you know, there is, you know, maybe a hole or something like that, and that's causing them to be a little blurry. Now, for GAN, they don't suffer from that, so they're quite happy to put mass on smaller numbers of places. In fact, I heard that you can compute, so people did very cute experiments with this, so they generated a lot of data from a GAN, and they started to look at when they started to see copies, or almost copies. And then with something called the birthday paradox, you can compute how many modes there are actually in this distribution. And these modes are very tight, so very, very tight modes. And it turns out that I think if n is the number of parameters, then n log n is the number of modes in that. So you can sort of generate n log n different data points. So that's a disadvantage, and people have worked hard to, you know, to improve that coverage problem. But I see that as the major sort of trade-off. So one of them is trying to cover a lot, the other one is about being blurry, the other one is not so worried about covering things, but then it's sort of focused its mass on a much smaller set of modes. And you can do things in between. So typically the best way to compare, you know, to connect them is through this Wasserstein autoencoder framework. You can look at the optimal transport problem, you can then move to the dual space, and then it becomes much more like an autoencoder framework, except for that the sort of the rate term is a bit different. I think that's very insightful of how these things are related.
Okay, unfortunately we should follow the schedule. Already 14 minutes back. So let us thank the speaker, thank Max for his very inspiring speech.